morning, sir.
Morning.
Sir, we can start our session at 9:05.
That's okay. That's fine.
Okay, sir. Okay.
Good day, then.
Good morning. Good morning, Professor Chakraborty.
Yeah, morning. How are you?
Fine. What about you?
I'm fine.
Yeah. So people are joining.
That's okay.
There
That's
is
okay.
some problem with WebEx app. Might be.
So yeah, so I joined using the meeting ID and the password.
Sorry?
I also joined using the meeting ID and
Yeah,
password.
yeah.
Clicking the link does not work. You have to use the
Yeah,
ID and
The link
password.
is not working. Yes.
Yeah.
Yes.
Because it was for day 1 only, I think. So it is
Acha,
maybe.
this is for day 1.
Yeah. That's why I think it is not working.
Okay. Hello. Yes, Mr. Siddharth. Hello. 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 Hello.
No, you are audible. I think the other side there might be a problem.
Sir, you are not audible, sir.
Professor Chakraborty, you can start. Already 63 participants are there. So
So you
please
can start, right?
Yeah, please start. Please start.
Okay, okay. Thank you. Yeah.
Thank you.
Hi, everyone. So let me share my screen. Please confirm if the screen is visible or not.
Yes, it is visible. Please make it
Okay.
full screen. Yeah.
Yeah, that will do.
Very nice. Very nice.
Okay, great. Okay,
Yes.
so yeah, welcome back, everyone. So yesterday, we concluded by talking about Gaussian distribution, like conjugate prior in specific. So we were discussing about, or we rather discussed about we discussed conjugate prior. And in conjugate prior, there were many advantages, right? The most important one is perhaps that you can get solutions in closed form, so the distribution is known to you. So this allows you to get distributions are
Okay, Professor Japoti, just 1 minute. Can you please all be on mute? Mr. Paramanand, can you please? Yeah, thank you. Yeah, Professor Japoti,
thanks.
please.
Yeah. So distributions are available. And when I say distribution, I mean the posterior distribution, right? In closed form. And this is the most important advantage of using conjugate prior, because if the distribution is known, all you need to do is just update the parameters. Like if you remember, we are updating the parameters of the covariance Sn inverse, and we are updating the parameters of mu n, and that's all. That's what we are doing. However, conjugate prior, generally we not recommend conjugate prior to be used until and unless there is a very strong reason. So generally, conjugate priors are not recommended. And why is it that these priors are not recommended if they are giving closed form solutions? The reason is that these are very strong prior. Okay, the reason is these are strong prior. And what do I mean by strong prior? To quickly recap, if you remember, we are finding out probability of theta given d, which is proportional to probability of theta multiplied by probability of d given theta, where this is my prior and this is my likelihood. Now, when I say strong prior, it means that this prior will have a significant effect on the posterior. For example, you remember the last example or the last case study we did yesterday. Our prior was Gaussian. Our likelihood was Gaussian with known beta, right? Both were Gaussian. Now with this setup, this is a conjugate prior setup. Your posterior was and will always be Gaussian. This need not be a good thing. Yes, it is a good thing that you are getting the posterior in Gaussian, which is a closed form. You only need to update the mean and the covariance. That might be a good thing, but it is very restricting that your posterior is always Gaussian. What if your data indicates that it has multiple modes? Your posterior will not be able to capture that. What if your data indicates that there is a support, that means it varies within a range, and beyond that it is 0? Your posterior in that case will not be able to capture that because it's Gaussian. So having strong prior is only recommended when you have very strong belief, which is often not the case. So therefore, generally strong priors are not recommended unless and until you have very strong belief. And if strong priors are not recommended, you cannot use conjugate prior from a theoretical point of view, because that will restrict your posterior, which means it can potentially give you wrong result. So therefore, conjugate priors are to be used with extreme care only if you have a very strong belief and that belief aligns with your conjugate prior belief, then only you should use it. Okay, so the advantage basically what it provides is outweighed by the disadvantage. So that is not recommended with extreme here. But and this creates a whole new series of problems. So that means, and the problem starts with not using conjugate prior. So that is when, or rather I should say without conjugate priors, it is almost impossible to get a closed form of the posterior. It is almost impossible, and impossible I'm underlining it. So without conjugate priors, it is almost impossible to get a closed form of the posterior. And why is it almost impossible? The reason is very simple. Probability of theta given d is equal to probability of theta, probability of d given theta. And this too is very simple. You can always multiply them. The problem starts when you always have this with the evidence. So in other words, probability of theta given d becomes intractable. It becomes intractable, so you cannot track it because of probability of d. Because of the evidence sitting in the denominator, it becomes intractable. And why this evidence makes it intractable? So how do you compute probability of d? Probability of d is computed as integration over theta, probability of theta, probability of d given theta, d theta. And this integration, remember theta is your parameters. I gave the example of ChatGPT, and ChatGPT has what? A trillion parameters. So you are looking at a 3 trillion dimensional integration in that case. Even for smaller problems, you are looking at a 1,000 dimensional integration or a 40 dimensional integration. And this integration you cannot do in 99.999999% cases analytically. So this is a high dimensional integral solution for which is not available in closed form. Okay, and that is the source of all your problems. If you can develop a technique for computing such high dimensional integral in closed form, you have cracked one of the major mathematical problems or mathematical open problems that exist. You just cannot. You can do numerical integration, but that does not help. You need to do it analytically to get an analytical solution. So I'm not talking about numerical integration. I'm not talking about some Monte Carlo integration, at least not yet. What I'm talking about is closed form, and in closed form, these integrals are all. I mean, this integral is almost impossible to compute. as I said, right? So we are stuck. So in short, we are stuck and we cannot compute probability of theta given d in closed form. So what to do? Okay. So one option, and the option I just told you, one option is to use sampling approaches, sampling based approaches, sampling based approaches. The idea of sampling based approaches is very simple. I'm sure all of you have done it at some point without probably calling it sampling based approaches. For example, if you have an integral like this, if you do finite element analysis, for example, you do some Gauss quadrature. So Gauss quadrature is a sampling based approach of computing integral, a numerical approach, where you take some quadrature point and then find out the integral based on those quadrature point. But Gauss quadrature we are not going to use, that is not scalable again. Okay, but the whole idea is that, can we draw samples? I don't want the closed form solution. Can we just draw samples from a distribution and represent the distribution with samples? And if we can do that, in most cases that is good enough. Okay, so sampling based approach, what does it mean? Okay, so sampling based approaches. Okay, and I think today whole day you are going to listen to sampling based approaches, if I'm not wrong. In fact, tomorrow first half, I think first session, I'm also talking about one of the sampling based approaches. Okay, so the idea is that I will be talking about two sampling based approaches in details today in this session, and those two are accept, reject or rejection sampling and importance sampling. But before I go there, I need to set the stage and talk about what sampling based approaches are, and what is the idea behind these sampling based approaches. Okay, so there is something known as the law of large number. Law of large number. And this law of large number, or LLN, not M, not large language model, law of large number. And this law of large number is basically what is going to allow us to sample and represent the distributions using samples. Okay, that is the whole idea. So what is law of large number is saying? That if you have to compute an expectation, okay, if you have to compute an expectation of a function gx with respect to the PDF of x, which is fxx. Now we know that from the definition, this is equal to integration of gx fxx dx, and it contains an integral, a high dimensional integral, because if x is high dimensional, this will be high dimensional. Okay. Now law of large number says that if you have enough samples, this can be approximated with samples. This will be equal to 1 by n g of xi, where xi is a sample drawn from f of x from the PDF. So law of large number allows you to represent the integral as a summation, to compute the mean based on this expression that is shown here. And this is nothing new. For example, suppose I have given you an unbiased coin, and I have told you that the coin is unbiased, but you need to prove to me whether the coin is unbiased or not. Okay, so I'll repeat. I have given you an unbiased coin. The information is given to you that the coin is unbiased, and your job is simple: prove that the coin is unbiased. Now, in common sense, what will you do? We'll toss the coin in number of times, and we'll calculate what is the probability of head and what is the probability of tail. And if both of these are very close, we can conclude that, okay, the coin is unbiased. But this is nothing but computing this integral using law of large number. When you are saying that you will compute you will perform large number of experiment, that is itself an use of law of large number, because you are never going to perform infinite number of experiments. You could never perform infinite number of experiments. So at the end of the day, you are taking decision based on some finite number of experiments. And that finite number can be large. It can be 1 lakh, it can be 1 million, it can be 1 billion. But no matter what that number is, it's a finite number. So you already use law of large number, at least because that's the common sense, but without probably realizing that it's law of large number. Okay, so this is basically the law of large number. And if I'm not wrong, it was proposed by Bernoulli sometime in 1780 or something like that. The date and the name might be wrong, but yeah, the law of large number definitely is not wrong. Okay, so this is basically the idea of law of large number. Okay, and to use this law of large number, what do we need? We need a way to draw samples from a given distribution. We need a way to draw samples from a given distribution, which is a non-trivial job. In fact, if I am very honest, there exists no algorithm that can actually generate true numbers that are truly random. Okay, so remember this, that drawing random variables, or drawing random numbers, or sampling, drawing random numbers, which is equivalent to sampling, is non-trivial, and there exists no algorithm that can generate numbers that are truly random. So in short, you cannot generate random numbers. So what do? We go for the next best thing that we can do. And the next best thing that we do is, so therefore, we work with pseudo random numbers. Okay, so therefore you work with pseudo random numbers, and all computer has this program of generating pseudo random uniform numbers, uniform variables. Okay, so what we do work with is pseudo random numbers. Okay, so how does it work? So I'm not going to talk about how the pseudo random numbers are generated, but we'll go with the assumption that, so we will proceed with the assumption that our computer code is capable of generating pseudo random uniform or pseudo random numbers or samples maybe from uniform distribution in 0 to 1. Okay, so we'll go by this assumption that our computers have the algorithm that can generate pseudo random samples from uniform distribution, and not just any uniform distribution in 0 to 1. And with this assumption, now our goal is that how we can generate samples from, let's say, the posterior probability of theta given d, because that is the focus. The focus is not on the computer side, science side of things, which is generating these random numbers. Rather, the focus is on the machine learning and statistics side of things, which allows you that, okay, this is possible, so now how we can do that. Okay, so that's the focus. So that means we are able to generate u from a uniform distribution, and the uniform distribution from 0 to 1. Remember how the uniform distribution looks like? It is 1 by b minus a. So in this case, it will be something like this. This is 0, this is 1, and this length is also 1. And so the area is equal to 1. And beyond this, it is 0. Before this, it is 0. So your computer code is able to generate numbers from such a random variable. And it's simple, right? You can think that every point is equally likely. Every point has the equal chance of being sampled. So this is possible. Okay. So now, with this setup, can we generate distribution? So now, with this is given, right? So now the question is, given you sample from 0 to 1, can we generate sample from fx x? So this is some PDF of x, okay? And the PDF of the x is known. Remember, the PDF of the x is known, but you don't know how to sample from that PDF. You only know how to sample from this u, and all you need to do is all you need is a process, an algorithm that can allow you to sample from this distribution fx x. And this is very simple. Okay, this is known as, so there is something known as the inverse CDF approach. Okay, remember what is given. You have been given x, not x, you have been given the PDF, right? The PDF is given. Okay, and you have been given some sampler which can sample from uniform distribution. What is your objective? Your objective is to sample x from this fx x. So this is kind of what is given and what the objective is, right? So this is the whole idea. So now, with this setup, the following things will be needed. Step 1, given fxx, which is the PDF, you compute fxx, capital F. Okay. Given fxx, you compute fxx, capital Fxx, which is the, so this is your PDF, probability density function, and this is your CDF, cumulative distribution function. Okay. So given fxx, you compute capital F xx. And then step 2, you bring your sampler into picture, you 0, 1, so you generate a sample. Okay. And step 3, your x will be equal to fx inverse of u. Okay. And this is quite intuitive. I can prove it, but I'll not go into the mathematics. Today, I want to keep the mathematics a little low. I think yesterday we have enough mathematics. So today I will keep the mathematics a little low. And I will rather focus on the algorithm without really going into the mathematical details in many cases. Because for yesterday, the mathematics was important, because to write the algorithm, you required the mathematics. Today, the mathematics is important for your understanding, but to write the algorithm, you do not need the mathematics. So I will not go into the mathematics. I will leave it up to you and your interest. And if you're interested, you can go through the mathematical part, but I will rather today focus on the algorithm part. Okay. Like the algorithm you see on the left, but I will give you the intuition. This is quite intuitive because fxx is my CDF, and we know that CDF varies in 0 to 1. Okay. And when you are generating a uniform number, that number is also varying in 0 to 1. You can understand that this will work. Okay. And then basically it is saying that the CDF, when you compute, if you do a inverse CDF of this, so when you do this, you get a uniform number. So it is basically saying that when you do fxx, you get uniform. So if you need x, you need to do fx inverse of uniform. This is kind of an intuition. There is a formal proof, which I am again repeating that I'm not going to that proof. Okay. But this is the step. These are the 3 steps. Just take these 3 steps and you can do sampling for any distribution. Okay. And clearly, because I'm using fx inverse, the name is inverse CDF approach. So the name is justified by step 3, the main step of the algorithm. Okay. Now, let us proceed further. So if this is so simple, why did I say that you are going to spend all the 4 sessions today, or majority of the 4 sessions for sampling method? I say so because there are some requirements that needs to be satisfied for using this algorithm. And what are the requirements? So requirements for using inverse CDF approach. Okay. What are the requirements? Let us see. And let us see and try to understand if those requirements will be satisfied in our case, which is Bayesian machine learning for now. Okay. So let us try to see. The first requirement is that you should have a sampler that can sample from 0 to 1. Is it satisfied? Yes. As I mentioned at the beginning, that we are going to assume all computers have an algorithm that can sample from the uniform distribution. Give me 1 minute, I will drink some water. Okay, so this condition is satisfied. Second condition is that we need fxx, and more importantly, we need fxx. That is the PDF. Is this condition satisfied? The answer is no, because we do not know the PDF. If I go back, as I mentioned, we don't know this. We only know the numerator. The denominator is not known. So we don't know the PDF in normalized form. We only know it in unnormalized form, which is not a PDF. It's just some equation. So this is not satisfied. Then third, even if you know fxx, its fxx should be invertible. You should be able to invert it. You see it here? You should be able to invert it. Is this satisfied for our case? Definitely no. If we do not know fxx, how can we know fxx inverse? In fact, in some other domains, there are problems where you do know fxx, but you do not know fxx inverse. So even that's a challenge, that you might encounter a scenario, not in our case, but in many cases, where you know fxx, but not the inverse. It's not invertible. In our case, it's more tricky. We do not know fxx at the beginning itself. So the third point do not even come into picture for us. Okay. What does it mean? It means that this indicates that inverse CDF approach cannot be directly used in our case. Okay. This means that inverse CDF approach cannot be directly used in our case, which means we will be using it indirectly. One thing that is clear, because I'm using the word directly. But how will we use it indirectly? That question remains, right? That question remains. So let us see. How can we use it? How can we use it indirectly? So let us see. So we want to use this inverse CDF indirectly. So basically what we need is, we want algorithms. At least one we need, right? But you will soon see we'll need multiple, that can sample from unnormalized distribution. So we need something that should be able to handle unnormalized distribution. And again, I'll underline unnormalized. So this means my probability of theta given d is equal to probability of theta, probability of d given theta, divided by probability of d, which is equal to, we're going to use some terminologies here. Okay. So we are going to write the numerator as pi star theta by z pi. Okay. And so probability of theta given d which we can also write as pi theta. This will denote my normalized distribution. Okay. And then we have pi star theta, which denotes my unnormalized distribution. And then we have our z pi, which is my normalizing constant. I think, can you please mute yourself? I think, yeah. Poonam, I think. So you are, yeah, normalizing constant. Okay. And this is intractable. This is not known. This is unknown. Okay. So that's what we are trying to do. We will only have access to pi star theta, and only by having access to pi star theta can we draw samples from pi theta. We need some algorithm for that. Okay. And we'll discuss over the next 1 year, 1 hour or so, maybe 2 algorithms. One is the rejection sampling, the other is the importance sampling. So let us start with rejection sampling. Okay. So one such algorithm is the rejection sampling. Okay. One such algorithm is the rejection sampling. Now, what is the high level idea of rejection sampling? Let us try to understand. The high level idea of rejection sampling is to draw samples from a tractable distribution. When I say tractable distribution, it means some other distribution which is known to us and from which I can sample. It can be a uniform, can be a Gaussian, and something like that. So their inversity can come into picture. Okay, from some tractable distribution, and we call it Q theta. And then only retain samples that satisfies the requirement of pi star theta. So that means what we are going to do, we are going to draw samples, and then we are going to reject many of those, but retain some, such that the samples we are retaining, they represent the target or the pi theta. Okay. Basically, what we want is that the samples that are accepted, the samples that are retained, those samples should follow pi theta. Those samples should represent pi theta. And because we are trying to devise an algorithm that primarily relies on rejecting sample, call it rejection sampling. And also, in other ways, you can imagine that some of the samples are rejected while others are accepted. So we also call it accept reject algorithm. Both names are fine. Okay. So how does it work? There is some intuition here. Let us see. So what we have our pi star theta, and this we will call as target distribution. Okay. Then we have our, let us see, Q theta, which we call as proposal distribution. Okay, let me make a small change here. Let's call it pi theta. Okay. Pi theta is my target distribution, and this is the distribution from which we want to sample. Okay. And then the proposal distribution. The proposal distribution is the distribution from which we can sample. There is a distribution from which we want to sample, and then there is a distribution from which we can sample. And then there is also pi star theta, which is basically unnormalized target distribution. Can you repeat? So let me check the chat. I think there is one question which vanishes. So let me quickly check the chat. Why symbol pi is taking and not okay? Pi in Greece stands for probability, or P. P becomes pi in Greece, and that's why the one who developed it used the word pi, because pi is P, P is probability. In that sense, there is, I mean, just that. Okay, but it's not that you have to use pi. Most book will use pi. You can use K, A, B, C, whatever. Okay, there is no one is binding you from using pi. But in books you will see pi, so I'm following that notation, because tomorrow if you look into a book you should not get confused. Okay. Similarly, same thing for Q. Q is a common thing that is used for approximate distribution or proposal distribution. And why Q is probably a more important question, because where is Q in the word proposal? So because P or pi is already used, so that's why Q is taken after that, because Q immediately follows P, MNOPQ, right? So in that sense, there is no reason. So unnormalized target distribution. Okay. So yes, it is also used for prior in many books. So pi star theta is unnormalized target distribution, and this expression is known for to us. Expression is available because I know the prior, I know the likelihood, so I can always compute, do the product and find out. The expression is available. Okay. So these are the ingredients that are available to us. Okay. Target distribution, proposal distribution, and unnormalized target distribution. Now, target distribution will not be using. So what we will be using is or are these two quantities. Okay. So now let us see what we can do, or how do we do it. Okay. So let me start drawing. So suppose this is my theta, and this is my, for now at least, pi theta. Okay. And I will use a color. So if the color changes, this can change. Okay. So, and let's say this pi theta, I don't know. This is my PDF. Okay. The one of the strange PDF I could draw, I draw it, and this is a PDF. So this is basically my pi theta. Okay. And I am not aware of this. Now, if you think carefully, your pi star theta is what? Z pi, which is a constant, multiplied by pi theta. If I go back, you will find it here, right? So this is your pi theta. So pi star theta is pi theta multiplied by z pi. And if that is the case, then, and this is a constant, we know that pi star theta will also be of same form, but it will be scaled. So you can imagine that pi star theta might look like, or it can be here also, depending on the value of pi. So z pi or z pi. So this is my pi star theta. So the main point is that the shape of pi theta and pi star theta, that is the normalized distribution and the unnormalized distribution, remains the same. The only difference is that in normalized distribution, if you can integrate, it should come to 1. In unnormalized, it will not come to 1. It will come to some other number. Okay. So you cannot solve this. But you cannot solve that anyways, but that's not a problem. But the important point, the take home message is that pi theta and pi star theta has the same shape. One is just the scaled version of the, or the unscaled version of the other. Okay. However you want to think about it. Okay. So we are only going to work with pi star theta. Keep that in mind. That's what we are going to work with. Okay. So now, let me again draw it. And this time we are only going to work with pi star theta. Okay, so let's start with pi star theta. It might not match exactly what I draw in the last slide, which is fine. But you remember that this is pi star theta. Okay, which is the unnormalized distribution, which is known to you. So you can actually plot it. Okay, this is theta. Now, along with that, you bring q theta into picture. So q theta will draw in let's say red color. Okay. Okay, but before that I need to do something. And let's say this distribution goes to 0 here. Okay, I'm forcing it to go to 0 either here or here, maybe here. So beyond this point, this is 0. And here also I'll force it just for the sake of explanation. So beyond this point, it is 0. Okay. So it is having a support. This might always not be the case, but for now, let us assume to understand the algorithm. Now, we need q theta. And q theta is something that you will decide. So let's say I will decide my q theta is something like this. Okay. So they are uniform. And this is my q theta. So now one question comes to your mind. Can you just select any distribution as q theta, or there are some requirements? Well, the answer is there are requirements. So can any distribution be selected as proposal q theta? The answer is big no. So what are the requirements? There is only one requirement. Q theta should supersede pi theta. Okay, or in this case pi star theta. And it means that this basically fundamentally means that if pi star theta is greater than 0, q theta should also be greater than 0. Okay, it should not happen that there is a case where pi star theta is greater than 0 and q theta is equal to 0. It cannot be less than, but it is equal to. And that's why you will see that I fixed this support here and then took the uniform which is superseding it. So as long as this distribution is greater than 0, uniform is also greater than 0, and then yeah, and then it can go beyond that. Okay, but so basically I cannot have a uniform from here to here, then it's wrong, then that's not a valid proposal. Okay, so I'm going to erase this. Okay, so that is the requirement. This requirement needs to be satisfied, that wherever your target is greater than 0, your proposal should also be greater than 0, and this ensures that you can sample from all areas. That is the reason. Okay, so this ensures that we do not miss any portion. This ensures that we do not miss any portion of what is it, pi star theta or pi theta. Okay, this ensures that we do not miss any portion of pi star theta. Okay, okay, so now let us proceed. So how do we solve it, or how do we sample it now? So now we have your ingredients. So first step is we scale q theta so that it creates an envelope over pi star theta. So the first thing we do is that we create, or we scale q theta so that it creates an envelope over pi star theta. Okay, how do we do it? So basically, let's take this color. What you will do is that you will multiply it by a factor so that it envelops this, and this I will call as multiplying factor. Let's call it m, m, and then it is q theta. Okay, so what we are doing is that we are creating an envelope. Now this can also go above, but the optimal one will be if you touch the peak, and this you can find out by finding the maximum of this pi star theta and then dividing it by q at that point. Okay, but you basically create an envelope. Okay, how is, you can decide your own method. There are n number of methods, but this envelope needs to be created. That is step number 1. Okay, so basically we have created m q theta. Okay, and you can one option is m is equal to supremum, which is the maximum of pi star theta by q theta. Okay, so basically the value of theta at which pi star is maximum, at that value you divide it by q theta. Okay, so in that case, so that you can create. Now that is step number 1. Now the main intuition is going to come now. So step 2, you sample from this. I mean, you need to sample from q theta. Okay, so sample from q theta. So let's call it what, q, which we are sampling from q theta. Okay, maybe q is not a right number because q and q will create confusion. So you sample Q tilde from Q theta. Okay, so you've created a sample. Let us go here. And let's assume that sample is this one. Just an assumption. It can be anything on this x-axis, but let's assume this point is the sample Q tilde. Okay, just for explaining. Okay. So now, what is the frequency of this sample Q tilde being selected from this MQ theta? What is the frequency of this sample, okay, being selected from this MQ theta? The frequency is this one, this straight line. Pardon, I could not draw a straight line, but yeah, somewhat. So this is the frequency. So this point will basically give you, and it is because it is uniform, it is same. Otherwise, it might not be. So this is the frequency. So this is what MQ of Q tilde, something like that, right? So this is the, maybe I should write theta to avoid confusion. Theta tilde theta tilde, and then in the next slide also theta tilde. Okay, this is better. Okay, so this is the frequency that which you expect that theta tilde will be sampled. That's what PDF is. In PDF, each of the y-axis denotes the frequency, x-axis is the number. So by definition of PDF, that is the frequency at which you expect to see theta tilde if you keep on sampling. Now, similarly, what is the frequency at which you expect theta tilde to be sampled from pi star theta? That is equal to this point. So you will take a line from here to here. So this point is giving you your what? Pi star theta tilde. Okay. Which means for every MQ theta tilde times, you should only select it pi star theta tilde times. And if you can do that, then that satisfies the condition that this theta tilde is coming from this probability. I'll repeat it. How do we know that a theta tilde or a theta sample is from this black probability? If it is selected with a frequency such as this. So now we are selecting theta tilde from this. But if we can ensure that theta tilde is only accepted as per this proportion, then we can claim that this theta tilde we are selecting comes from this black distribution and not from this orange distribution, because by rejecting samples we have ensured that theta tilde will not satisfy this criteria but will satisfy this criteria. So it will not satisfy but satisfy this criteria. This is the philosophy of rejection sampling, that you sample from this but then you reject it so that this sample is only accepted following this probability and not following this probability. Okay, but how do you do that? To do that, what we do is, let me bring another color into picture. This line is your PDF, right? So you consider a uniform distribution here. Okay, and you sample a uniform distribution in this range, and you only accept it when that sample is below this point, and you reject it if that sample is above. That ensures that you are only accepting theta tilde proportional to this black frequency. Okay, So I'll repeat it. So what you do is that I'm rotating this. Remember the color, rotate. So I rotate it. Okay. This is my 0. This is my M, Q, theta tilde. What I will do is I will generate uniform distribution, and from uniform number uh, with following uniform distribution in the range 0 and M, Q, theta tilde. However, there is something sitting here, which is my pi star theta tilde. This is my pi star theta tilde. So then we'll only accept if this uniform number is less than this. That is, it is in this region. If this uniform is greater than this, that means we are going to reject it, because greater than means in this region, less than means in this region. But how the algorithm will look? Algorithm. What is given? What is given is pi star theta. The expression is known to you, and you have assumed some q theta which satisfies all the criteria. Okay. Step 1, you sample theta tilde from q of theta. And how do you sample? Inverse CDF. Okay, which you probably know, don't you need to use, it will have, you already have some inbuilt codes for that, but you sample from that. Step 2, you sample uniform u from a uniform distribution, and that is in the range of m 0 and m q theta tilde. Okay, and then you check if u is less than pi star theta tilde, then you accept theta tilde, else you reject and you can't, else reject, else reject. Okay, and this loop continues until you have enough samples. So as simple as that. You sample from the proposal, you sample from the uniform, and then you check whether this is less than or greater than, and then if it is less than, you accept or you reject. There is another form of this algorithm, same thing but a little bit less tedious. Same thing, you sample theta tilde from q theta. Step 2, you sample u, but this time from 0 to 1. And then 3, if u is less than pi star theta tilde divided by m q theta tilde, then you accept theta tilde. Actually, this is the probability, so wait. Probability pi star theta tilde, this is known as acceptance ratio, m q theta tilde. Else reject with probability 1 minus. You can clearly understand both are the same things. I'm just scaling it to write it in terms of probability, and that's all. But the algorithm remains the same. And it is useful because every time you now sample from the same thing, previously for a new sample, this will change. And so you need to sample from a separate uniform. In this case, that issue is not there. That is handled by this ratio A. Okay. So this is your rejection sampling. You select sample from Q and then you reject it based on certain criteria so that the accepted samples start following pi theta. And that's all. Okay. Show any questions on this? Any questions on this rejection sampling? Because next I will start with important sampling, and that will be basically the end of this session with important sampling. Yeah, any questions? Maybe you can type if there is an echo. Okay, let me open the chat. You can please mute yourself. Okay, I'll read the chat. Okay. Sir, in rejection approach, what proportion ratio of rejection returning distribution to achieve the target? Yes. So it's very simple. Let me go back. The summary is this, by the way. The other question was summarize. This algorithm is the summary. This is all we discussed till now. Okay. Okay. So now coming back to the proportion. So let us take this diagram and understand. Okay. And I will take 2 points. Some color I have not used, maybe green I don't see. So you think if I have a theta star here and a theta star here, which of these two green is more likely to be accepted? Obviously this one, right? Because this has a higher frequency. This is almost negligible in frequency. So the proportion in which we accept should be this ratio divided by this ratio. So this, let us call it A, and this black, let us call it B. So the proportion should be A by B, which is pi star theta star divided by MQ theta tilde. And then you can, if you that is the case, then you can easily think that at this point this ratio will be very small. So most of the samples here will be rejected. Whereas here almost all samples will be accepted. So the proportion in which samples are accepted or rejected is the ratio. Which ratio? This ratio. Okay. So the proportion is this ratio. So to summarize once more, what we do is we start with we want to sample, but we cannot sample because the normalizing constant is not known. So as the normalizing constant is not known, what we do is that we sample from some known distribution, which we call as the proposal distribution. And then among those samples that we get from the proposal distribution, some of the samples I retain, some of them I reject. And how do I retain or reject? Based on this condition that you see here. And that is your rejection sampling. Okay. Okay. Now clearly you can understand one thing, that in rejection sampling, many of the samples are going to be rejected. Many of the samples are going to be rejected. The reason is that that's the whole idea. And if you don't select a good proposal, even more samples will be rejected. So selecting a good proposal is important. And no matter what proposal you select, your samples are going to be rejected. Okay. And that becomes the motivation. So one limitation of rejection sampling is that many samples are rejected. Okay. One of the limitations of rejection sampling is that many of the samples are rejected. So this brings us to an important question. Can we not devise a method that will allow us to accept all samples. So that means, can we not increase the efficiency of the sampling scheme? Because rejection, so suppose I want 10,000 samples. Now, if my acceptance ratio is 0.1, that means I am sampling 100,000 samples, and from there I'm selecting 10,000 samples, right? But if my acceptance ratio is 100%, then I only need to sample 10,000 of those. So that means ideally I will want no samples to be rejected. That's what I will want. So how can we achieve that? How can we achieve a scenario where uh, where all samples are kind of accepted? And important sampling is the answer. So that is the next thing we'll talk about. Important sampling is the answer. Okay. So let us talk about now important sampling. Okay. So with that, let us start talking about importance sampling. By the way, even for rejection sampling, there can be a proof to show mathematically that you get sample from exactly what we desire. But again, as I said earlier, that today I'm not going to the proofs and derivations today. The reason is that those proofs and derivations are not needed for writing or using the algorithm. Yesterday, the derivations are needed for writing the algorithm. So that is why I was doing those tedious derivations. And yeah, those derivations are not difficult if you do it once on your own. But if you only see and listen, then they sound very daunting. Anyways, so yeah, so the derivation I'm not doing today. Okay, if you're interested, you can write to me. I can refer you to my own video lectures where we have done the derivations. Okay. So next is importance sampling. Okay. So before I talk about importance sampling, you need to remember that in machine learning, most of the times we are interested in computing expectation. That is what mostly we are interested in. If you think about it carefully, you realize it. And I will show it to you also. So we are mostly interested in maybe computing integration, I mean expectation, right? Expectation, let's say, with respect to pi, okay, of some function g of theta, which is equal to integration of g theta, pi theta, d theta. This is what mostly we are interested in, okay? And this you can understand because remember that while our ultimate goal is to compute the predictive distribution, and the predictive distribution was the integral with some PDFs sitting there. So the predictive distribution was actually nothing but an expectation. Similarly, law of large number I talked about. The law of large number is nothing but a law for computing expectation. So you will so almost all the times what we are interested in is to draw samples, but draw samples for computing our expectation using law of large number. That's what we are primarily interested in. Okay. So let us start by this. Now we want to compute this, right? We cannot compute this. This is intractable because theta is high dimensional. That is one way of looking into things. And this is also, you cannot sample because, and also this is point number one. Point number two is, it is difficult to sample from it's difficult to sample from pi of theta. Okay, or almost impossible. So we cannot sample from pi of theta, so we cannot use the law of large number. So basically we cannot use 1 by n summation g theta I, because we cannot draw theta I. So we cannot use that. Okay, and what to do? And this is where important sampling comes into picture. Okay. So remember that our objective is to compute g theta, pi theta, d theta. Okay. Can we not write it as integration of g theta? G theta is known to us, and then pi theta by q theta multiplied by q theta d theta, where q is something I can sample from. Distribution from which we can sample. Okay. So this is a distribution from which we can sample. So now this quantity is sitting here. Let us give it a name. Let us give it a name. What name? We give it a name of W theta. Basically, this is a weight. So with that, now what do I have? G theta, W theta, Q theta, D theta. And this together, this is a weighted G. So I can call it G, W theta, Q theta. Okay. If you want to compute, if you don't want to compute, you can directly go with that. And now it's easy. This because this is nothing but expectation of with respect to Q. Previously, the expectation was with respect to pi, from which I cannot sample. It's with respect to Q, from which I can sample. And then I have what? W theta, D theta. Okay. So you basically scale it and use a different sample, this different distribution from which you can sample. And in this case, the important point is that whatever samples you are drawing from Q theta, everything is used. There is no rejection step here. Everything is used, but used after weighing it. There is a weighing factor that is coming. So each sample is weighed, but not rejected. So there is zero rejection in this case. Yes, some of the weight can go to zero. And in that case, you can say that it is rejected. But in general, I mean, nothing is getting rejected. Okay. So this is basically my important sampling. Okay. And so after this, what I can do is very simple. This is basically equal to 1 by n summation W theta I G theta I, where theta I is now from Q theta. Q theta is my distribution. I can sample from that. So this is important sampling. So this is importance sampling, but this is of no use to us. At least the way I have discussed it. This is of no use to us. Can someone write in the chat box why this is of no use to us in probabilistic machine learning? Can you think and tell me why it is of no use to us? Why is it that we cannot use it for our purpose? If you open the chat box and see if someone is able to answer. Why is it that this expression, this important sampling that we discussed, is no, the results will be good. Results is not an issue. I said no use. No use means you cannot use it. Forget about get result. You cannot use it in the first place. So the reason is that it is using pi theta. Pi theta is unknown to you. How will you use it? Our whole objective is that pi theta is unknown. We know only pi star theta. In this case, I derived everything with pi theta. Pi theta is not known. And if pi theta is not known, you cannot use it for Bayesian machine learning or probabilistic machine learning. Clear? Why is it is of no use? So this is important sampling. However, it is of no use to us. Okay. However, it is of no use to us. And the reason is that pi theta is not known. Designing, not getting a good sample, all of those will come later. First of all, you need to use it. Once you can use it as an algorithm, then all those aspects will come. That how to get good samples, how to get very good match, how to converge quickly. All of those will come later. But right now, the way I have discussed it, you cannot use it. Pi theta is unknown. So what to do? So there is a, so let us now try to see if we can extend it and make it usable for our case. So can we use important sampling when only pi star theta is known? So let us try. Okay. So what we are trying to find out is expectation with respect to pi of or g, of g theta. This is what we are trying to use, right? This we already know is equal to integration of g theta pi theta d theta. We know that. Now we know that pi theta is not known, so we need pi star theta. So what we'll do is g theta, and then pi theta is equal to pi star theta by z of pi d theta. This is equal to 1 by z of pi, that is a constant, comes outside the integral. What you have is g theta pi star theta d theta. Okay. Now let us bring important sampling into picture. So this is equal to 1 by z pi. I'm not going to touch it right now. Integration of g theta pi star theta by q theta d theta. Okay. And this is my w star theta. W star because unnormalized pi star is sitting there, so W star. Previously I used W. So then this is equal to what? 1 by z pi, and then this is basically expectation with respect to q theta, and expectation of what? G theta W star theta. And at least now the numerator is fine. I can draw samples from q. I know pi star theta, so I can compute W star theta, and G theta is anyways known to me. The problem element, however, is this one sitting here. So let us look now at try to attack that. Let us now try to attack that. So then z pi. What is z pi? It is a normalizing constant. This is basically nothing but integration of pi star theta d theta, right? Because with z pi in this form, this ensures that integration of pi theta d theta will be equal to 0. So basically we know that pi of theta d theta integration is equal to not 0, 1. So therefore pi star theta by z pi d theta is equal to 1, which is therefore integration of pi star theta d theta is equal to z of pi. So this is what I am using here, right? This is what I am using here. So now, as we are using it here, now what will we do? We'll do the same trick. Integration of pi star theta by q theta multiplied by q theta d theta, which is then equal to integration of w star theta, right, q theta d theta, which is basically expectation of with respect to q of w star theta. So therefore I can take that and substitute it here, and that will basically give me expectation with respect to pi g theta is equal to expectation with respect to q w star theta g theta divided by expectation with respect to q w star theta. So now this is something that we can use in our, yes, this is something that is now usable. This is something that does not require pi theta but requires only pi star theta, and you can directly use it for solving or for sampling or for computing expectations. Okay, so that is now possible. This is known as normalized importance sampling. Okay, now again you can show that the usual importance sampling is an unbiased estimator. So there is a math and you can prove it that it's an unbiased estimator. But normalized importance sampling is not an unbiased estimator. So that can be shown, but it can be used in Bayesian inference. Okay. So that actually completes my part, but I will go through the slides that I have. So let us see, let me come to the laser mode. So this is what we are always interested in. Remember the Bayesian thing. And in Bayesian thing, this is the integration we like to calculate, and this is high dimensional, so that makes it intractable. So you cannot sample, you cannot find it in closed form because this integration you cannot compute. That's where we started, right? That the evidence, the denominator is intractable. So if you don't use conjugate prior, you cannot find out the distribution, and that is problematic. So as a result, I mean, this is what we are interested in, the mean and all those things. And then here is one example which you can read on your own, but this is a similar example that what is the probability that he will hit this red circle, and that comes out to be basically the ratio of this area by this area. So you can go through it. Yeah. So basically this is an example that shows you the Monte Carlo way of doing things. If you want to find the probability you will hit this red circle, you do n number of experiments and then find this ratio, and that's your probability. Okay. And there is some statistical derivations for that which I skipped. which I skipped. And then here, this is important. So you can represent, use the law of large number to represent, this is the law of large number, and you can represent it, the mean, using this, and this is unbiased estimator. That proof I have not shown you, but you can see. Okay. And then similarly, you can represent distribution by use the direct delta function. So that is like each of the points, and that represents your direct delta function. But the important points that I want to, the most important thing is this one. So when you are sampling, this is what you are looking at. You are trying to compute expectation by using samples drawn from pi x. But how do you sample from pi x? That's what we started, right? How do we even sample from pi x? We have only algorithms for generating pseudo random numbers, and most algorithms rely on the pseudo random numbers for uniform in 0 to 1. Okay. And then how to sample from a continuous distribution? We talked about the inverse CDF, right? Inverse CDF approach, which is somewhere. Okay. The inverse CDF approach is not shown here, it seems, right? Let's see. Have I shown the inverse CDF approach? Probably not. So the inverse CDF approach is not there, which I covered. But yeah, here it is. So you can, there is the inverse CDF approach, right? You can use this to sample from any distribution, given that you know the PDF, you know the CDF, and the CDF is invertible. So if you do that, you can find it out. And in multivariate case with conditional, you can also use this, but this is still valid for everything as long as you can invert it. Okay. But that we cannot use in our case. And the reason we cannot use it is because very simple. We do not know pi. We do not know our target distribution. And if we do not know our target distribution, how can we even hope to use any of this? So that inverse CDF approach cannot be used directly. And so we need sampling approaches. And that brought us to the accept, reject, or rejection sampling, where what we do is very simple. Where is the algorithm? So the same plots that I did is shown here. This is the reject portion. This is the accept portion. We computed this ratio. And this is the algorithm. You sample y from q of y, u from this. And then you accept with probability this. If this is satisfied, otherwise you reject and repeat. And this continues. Okay. And this, along with that, I gave you another alternative algorithm where you sample from 0 to m q star. Okay. This is the proof that I was talking about. I did not cover it, but you can prove it that this actually gives you sample from what you desire. Okay. And yeah, and this is a kind of summary of inverse CDF and accept reject sampling. But this, many of the samples are rejected. So is there a way to find out samples drawn from proposal? And we talked about that already. So that brings us to the important sampling that we talked about. And in important sampling, this is what we are interested in. You divide by Q, you call it the weight, and this you get an expectation. And this expectation you can represent using law of large number. And you can because you can sample from Q. That's easy. Okay. This is the proof that this is an unbiased estimator. Again, for you to read, I did not cover it because this is not needed for the algorithm as such. This is for just for building, not just, but this is for important and for building conceptual clarity. This is one example. The MATLAB implementation is given here. So when I share, you can look into the MATLAB implementation. Here, your objective is to sample from a multivariate Gaussian distribution using importance sampling. And this example shows how the importance sampling code works. So this will be shared with you along with the slides, and you can go through that. And this basically shows you, like if you do standard Monte Carlo, many of the samples are here and there, whereas in importance sampling, everything is very close. So it reduces the variance. There is an optimal importance sampling, which is of no use, no practical use, but just some mathematical derivations. But yeah, recently we are trying to use it in deep learning sense, but that's not for today. And then we talked about that in Bayesian machine learning, none of this can be used because pi is not known. You only know pi star. So for that, there is normalized importance sampling. that you can use. And in normalized importance sampling, after doing all of these calculations, um, where is it? This is what you get. Okay. And this can also be used even if Q star is known only up to a proportionality constant. That part I've skipped, but that is not practical, but more of some mathematical exercise. Okay. So these are the things that we have discussed. Again, prove that it is not unbiased, and then the summary of the whole things. Okay. And one important thing is that this is embarrassingly parallelized, so you can use multiple CPUs, you can throw that and all of those things. Okay. But importance sampling also has limitations, which in the next session, not me, but someone else will talk about Monte Carlo, I believe. There you will see about Markov chain and all those things and how those can be used for sampling from this kind of distribution. Okay. So I'll stop here. If you have any questions, I will be happy to answer. Otherwise, we are done for this session. If you have any question, you can type it. Yeah, Gibbs sampling will be in the next session, because Gibbs sampling is a type of metropolis testing. So that will be covered by whoever is teaching metropolis testing will also cover Gibbs. If not, tomorrow, I think same time, morning session, I'm teaching Hamiltonian. If Gibbs sampling is not covered until then, I will cover Gibbs sampling. But I believe it will be covered in the next session.
Yeah, thank you, Professor Chakraborty. Actually, today I'm having the plan of covering that Gibbs sampling as well as implementing all this rejection sampling, importance sampling, and all these things using Python. Small codes, so that they will be having a kind of feeling of that exactly what we are doing, because so many big equations. And I'm telling you all that so many big equations we are seeing. Okay, but when we are going to code it, it will be very easy, very easy, because we will be using Python coding language. So you have to basically understand the logic, exactly how the sampling is being done, how this particular proposal ratio is being calculated, and those are really very easy to implement. Okay, so but the thing is, the main complexity, main challenge is understanding the mathematics. Once you can understand the mathematics, it is very easy to implement. Okay, so this is the assurance from my side, and I'm telling you repeatedly that this is my objective only, to have this particular program, so that you'll be understanding, or I can make you palatable, all these things palatable to you. Okay, so that you can actually understand that all these kind of mathematics, whatever we are doing, it is implemented in a very easy way. Okay, that implementation is not that much difficult, but yes, the derivations are actually difficult. Derivations you have to actually understand. And that recognition power, yesterday I was telling that by looking at the distribution, can you recognize that which distribution it might be? It might have some.
That is very important.
Yeah, so that is basically matching the distributions. Okay, and we'll be actually delving into this, especially in deep sampling. You'll be finding that understanding that looking at the posterior, can you understand that what kind of distribution it is? Okay, so there will be some forms by which you can actually understand, and these are very simple algebra. Very simple algebra while you are deriving these things, like completing the squares. So we used to do all these things from class 7, 8. Okay, whenever we started this linear algebra, we used to do this quadratic equation and all these things. I think quadratic equation started in class 8. So those completing the square. So that is actually very important to understand. And these are very easy. What you need to there should be somebody who can hold your hand to in this particular journey. That okay, you are going in correct way. Okay, so that is the thing. So let us do that in the next. Means I'll be taking the sessions after lunch, where I'll be discussing all these things, how to implement actually. Okay, thank you, Professor Kurti, once again. Coming from your busy schedule, you are actually spending time with us, means educating us. Thank you, thanks a lot.
And I will share the slides all together maybe after tomorrow.
Yeah.
And the codes codes are integrated into the slides which they can refer.
Yes. Acha, another thing is that yeah, regarding yesterday's session 4, we have actually lost the video. Means due to some technical problem here,
Oh,
we couldn't record it. Okay,
okay.
so but we'll be having these lecture slides, and you
That's
have
all.
already described. You have already described hand scribed notes, so I think that will not be a problem.
Also, I
And
think it is recorded on my website when I taught it, so that can be referred if
okay,
needed.
yes. So you can
So that can be
actually,
referred if needed.
yeah, that also can be referred. That also can be
Yeah,
referred.
yeah,
That is a very good thing actually Professor Chakraborty is doing. He's recording all the things, and these
yeah.
records are very, these are assets for life.
Okay,
Yeah.
okay.
Thank you. Thanks a lot once
Thank you,
again.
thank you. Okay, bye.
Thank you. Bye. So we'll be joining again at 11:15. Where Professor Rajesh Kumar from our institute, as well as he is now on deputation to University of Johannesburg. He is actually holding a professor position there. So he'll be joining from Johannesburg. He'll be taking the session on Markov chain and this Markov chain Monte Carlo, then Metropolis sampling, Metropolis Hastings sampling, and if possible, then Gibbs sampling. Because these are now we are now entering into the you can say the core of Bayesian, that how actually we should implement all these things in computer, because you are not going to by the way, you are not going to calculate it by hand. It's not possible. So we'll be actually using computers to implement all these things. And in the after lunch, I'll be coming with all these implementation, small problems. Okay, so we'll be generate some data, and will be actually in statistical modeling. It is you have to actually understand that if there is real data available, then it is very good, but that also you need to know what is the ground truth for that particular data for predictive purpose, prediction, because you are testing your knowledge through modeling, and this modeling is basically implemented using Python. Okay, so you need to have some kind of synthetic data based on which you can test your that whether you are correctly modeling the things or not. Okay, so I think this will help you. And please ask questions whenever you are not understanding something. Okay, please ask question. We'll be very happy to answer you. Is it okay? Okay. Okay, so we'll meet again at 11:15. Okay, the next session will start at 11:15. Okay, thank you. Acha, regarding the session, this is yesterday's WebEx session. This is day one's WebEx session. So let me just ask in our EICT Academy that how to actually join today's session, means day two session. Okay, and we might give the link in WhatsApp group or in the Canvas. Okay, so please follow that. Okay, thank you.